So firstly, what you have to do here is to get the data inside. So I'm going to use this data from the University of California. So it's admissions data set basically. If you see, it has 4 different columns: admit, GRE, GP, and rank. So it basically tells a story if a student is getting admitted or not based on his GRE score, based on his GP, and based on the rank, right? First things first, what we have to do here is to make a decision of what we need to predict. So again, let me open it. This process, let's just go ahead and predict the admit based on GRE, GP, and rank. So in that case, we need to make sure admit is being read as a categorical variable. So if I run my summary command, if you see here, there is a quick problem. Not a problem, actually, it's just a change that you have to do in the data. So you have the variables listed out here. GRE is continuous numerical, GPA is numerical, rank is categorical, and as well as admit is a 2-level categorical. So today we're going to talk about binomial logistic regression that's going to help you to predict your 2-level categorical variables. For example, 0, 1s, true, false, male, female, and so in this one, admit is basically 0 and 1, right? But right now it has been distributed as continuous. So what we have to do here is we have to change that into a factor, right? Before that, let me show you guys what I'm talking about. So if you see here, the frequency of zeros in the data set is like around 250-ish, and the frequency of ones in the data is around like 220-ish, like that, right? So it's like either 0 or 1. There is no other value in between. You see here? So this should be treated as a factor. And our algorithm is going to be predicting on top of your admit column. It's going to give you a prediction in terms of either the student is going to get admitted or not based on the the future data. So what we have to do here is to make the conversion. Just gonna use that. So alright, so now that it's been converted as a factor, now if you see your summarize, now it's perfect. Now if you see the difference, now it's been it just shows the frequency again, right? So this is exactly how it should look like. So now let's go ahead and do the partitioning. So for partitioning, I'm going to be using this caret library. I've already installed this package, so I'll just go ahead and point to that package. And then first I'm just gonna create my training data set. So first thing, I need to create my training indexes before that, right? So I'm gonna use a create data partition function that is been built within the caret library. What this function is basically requiring is for you to specify your y variable. What is the split between your training and testing? So I'm going to say, like, my training should have like 80% data set. So I'll just say 0.80 p is equal to partition is equal to 0.80, it's just 80%, and I'm going to say list is equal to false because I don't want my indexes to be listed out, right? So alright, so now that I have created my training indexes, this is the first step to do the partition. Now let's go ahead and create a training data set, right? Which is super simple. I'm just going to use my data in, and the data is, the indexes will be chosen from the training indexes, and it's going to include all the columns. When I just hit a comma and I don't include anything after, it's going to include all the columns, right? So I'm just going to control enter. That's done. Next thing is going to be my testing data set. So again, I'm just going to use my data in and exclude all the training indexes and include all the columns, right? Perfect. So if you wanted to know more about the indexing, I have created another video in my channel itself. I have put it as a card, so you can take a look into that video to understand more about the indexes. So now that I have my training and testing data set, let's take a look into see the split. So the training has 321 observations, testing has 79 observations. So let's go ahead and build the model here. I'm just going to name the model as my model, and then the function that I'm going to use is GLM, right? It stands for generalized linear models. I'm just going to use my admit as my output variable, and then I'm going to use everything else, GRE, GPE, GPA, and my rank as my input variables, right? So I'm just going to say dot because it's going to include everything. So just say dot. Then the data is going to be training data set, right? And the next argument is called family. So family, I'm going to say binomial, since I have only 2 levels or binary in my admit, which is only zeros and ones, so it's binomial, right? So there is also other quasi binomial, poly regression. There's different other families, especially if you want to deal with multi-level categorical variables, you can use those families. So this one, admit, is just a 2 level, so I'm just going to use binomial, right? All right, so my model is built right now. All right, so the results are here. So you have your function call, then you have your deviance residuals, and then the important thing here is the coefficients and the deviances here. So the coefficients, as you know, it just shows you the intercept, then the slopes of the GRE, slope of your GP, and slope of your rank, right? So you can basically form your equation like this. Admit is equal to minus 2.27 plus 0.001 into GRE, and then 0.484 into GPA score, then minus 0.540 into your rank, right? So if you see here, it also shows a standard error corresponding to these estimates. So you wanted to always have, it's an error, right? You always wanted to have the error as less as possible. So that is why you do a z-test, which is going to be basically a ratio of your estimate on your standard error, and then you also have your probability corresponding to your z value. So this probability or the p value, this shows basically how much of influence does the standard error has on these estimates. You always wanted to have this p value as less as possible. It's easy to identify here. It just shows your stars here. So when you have 3 stars, which means it's the lowest, so it's gonna range between 0 and 0.001. And on the bottom you have your deviances, you have your null deviance, and you have your residual deviance, right? So what is this null deviance first? So null deviance basically means that when you're predicting your output, you're only going to include your intercept. You're not going to include your GRE or GP or rank. So what that means is admit is equal to minus 2.27. That's it. You're not including any of these. That is on 320 degrees of freedom. What does this mean? How do you compute? How does this 320 come into play, right? So it is basically n minus k minus 1. N minus k minus 1. So n is the number of records in the data set. In our training, as we know, it has 321. So 321 minus k is basically the number of variables you include. So because it's null deviance, there is no variables. You're not including any of the variables, right? You're only going to introduce the intercept. So n minus 0 minus 1, which is basically 321 minus 1, which is 320, right? And then the residual deviance, you're gonna this is the deviance of your predictions after you're including all the other the variables. So this score is 376.33. The degrees of freedom is 317. So which is because you have 3 other variables included with this. The k is equal to 3 in this case. So that becomes 321 minus 3 minus 1, which becomes 317, right? And then you also have your AIC, Akai Key Information Criterion. So Akai Key Information Criterion should be the least as possible. The least that you have, the better the predictions are. So right now you have 384.33. What we can do is basically to drop GRE and GPA from your model building. since rank is the only one that has a good p-value, let's try to drop GRE and GPA and to see if these deviances are all going down. Let's do that right now actually. In fact, I can just snip this out. Let me just snip this out to show you guys what we had before. This is what we're going to have pretty soon. Alright, so if you see, so this time I'm just only going to include admit based on my rank, right? So when I run this, and then when I run my summary on my model, let's see if the Akaike information criterion and my deviances are reducing or not. If you see here, my AIC score doesn't go much, but it has increased by 3, but it's not a big one. But my residual deviance has gone by 7 units. My AIC has increased by 3 units. So which is not a big difference if you see here. So I'm just gonna use those 2 variables back. So I'm just gonna use this to build the model. So I'm not gonna drop any variables, because only if I have a good decrease in my AIC or on my deviances, only then I'll take a decision of dropping those variables, right? I might as well keep them. So next thing what you have to do is, once the model has been trained, now it's time for predictions. To understand the predictions, let's go ahead and create a prediction function. So predict train, so that is equal to predict. Predict is a function to determine the predictions. So I'm just gonna say, hey, take the predictions from my model, right? And data, it's gonna be train underscore ds, and then type is equal to response, right? Alright, so now we have got the predictions. You can also even take a look into that. I can show you guys. So if you see here, these predictions are pure probabilities. The probability of the predictions, that's exactly what it is here. You see here, it's going to range between 0 and 1 since it is probability. So alright, so I'll give you an example here. Let's take a look into the first data set. The first person here with this GRE score of 380 and GPA of 3.61 and rank of 3, he has 0.1% probability that he'll get selected or he'll get the admission. This is basically what the data is also telling. The second person with the GRE of 660, GPA of 3.67 and rank of 3, university rank of 3, he's gonna have 0.3% probability of getting selected. So it shows different probabilities. We don't know the accuracy yet. So let's go ahead and look into the confusion matrix to understand the accuracy. So how do you do that? Is using this table command. So I'll just say actuals is equal to my train. This is my actuals and my predictions. Predictions is equal to my predicted train. So here I'm going to do an assumption. I'm just going to say that hey, take all the predictions, and if it is greater than 0.5, make it as 1, and if it is less than 0.5, make it as 0, because my I'm comparing my predictions, these numbers, with my actual data, right? My actual data is basically on, if you see, it's only zeros and ones, but I wanted to change these ones, these probabilities, into 0 and 1s. So how do I do that? I'll just say here, if it is greater than 0.5, make it as 1, otherwise it's make it as 0. So you can either do this, or what you can also do here is you'll just create train binary is equal to, you can put like an if else it's just easier to understand if you're especially new to this. So you can just say if it is greater than 0.5, make it as 1, else make it as 0. So this is the if condition, 1 is the if condition, 0 is the else condition, right? So you can either do this or do this, write this, it's the same thing. So I'm just gonna do this right now, this shortcut. Let's just go ahead and run it. So if you see here, what you see on the bottom is your confusion matrix, right? Basically intersection of your actual values versus your predicted values. So 0 means the student is not getting admitted. Likewise, false in the prediction means that the student is not getting admitted. Likewise, 1 is student admitted and true is basically student is not getting admitted. So let's see the comparison. So in actuals versus predictions, I have that 206 times I am predicting that my student will not get admitted, and he is indeed not getting admitted, right? And then 19 times I'm predicting that the student will get admitted, and it is actually being true that the student is actually getting admitted, right? So if you wanted to get the accuracy, it's what you can do here is it's basically like the correct predictions are these two, right? So the 206 and the 19 are the correct predictions. So these are the true negatives and these are the true positives. So I'm predicting that the student is not getting admitted, which is actually that's the fact. So that is 206 plus 19, which is basically I'm predicting that he's getting admitted, and indeed he's also getting admitted. So 216 plus 19, with 206 plus 19, and that should be divided by the total number of records that I have. So totally I have 321 divided by 321 will give my accuracy. So I have 70% accuracy in this training. So I can also calculate the misclassification rate, which is basically I can just take the 13 plus 83, right, divided by 321, which is basically misclassification rate is basically the 29%, right? If you don't want to do it by hand, you can also do like a diagonal command. How you can get this accuracies? You can just run like a sum diagonal function, and then pass your table inside, right? You just pass this table inside this function, and then that's going to give you the diagonal score 206 plus 19. It's going to sum up these, and then if you just wanted to get the sum of the full table, just remove this diagonal, and then then that should work. Perfect. And then just just run that. That's going to give you the full total, which is basically you don't have it because you know that you can just run the nrow command for your training data set and get that. It's same thing. Now that we have this, let's go test the model using the testing data set. In this case, I'm just going to again use the same model, but then the data is going to be testing. That's the only difference that I'm going to do here. And then the type is going to be again response, right? Let's go ahead and run it. So now I have my predict test. Let's again similarly, let's go ahead and build this confusion matrix to see how the model is performing in the testing data set, which is a new data set. The model hasn't been experienced with that. So this is an important thing to determine if my model is performing good or not. So I'm just going to use my actuals as my testing data set and my predictions as my predict test, right? Let's go ahead and build that confusion matrix. Alright, so if you see here, the accuracy is that. So 52 plus 7 is 59 divided by 79. So 74% accuracy, which is a little bit better than my training accuracy. But I just wanted to see if I can improve the score a little bit better. How do I do that? I can only do that by changing this number, right? I can either manually change this to 0.3, to see what the accuracy means, if it is any better, or I can just keep on going to see if that will create any kind of impact for me. But all that I need to make sure is my accuracy is increasing. In this case, looks like the accuracy is going down if I go beyond this. So you'll keep on, like, you can either manually, like, up, increase or decrease this number until 1. You can do it, and from 0.1 until 0.9 you can increase or decrease this number to see what is your accuracy score here. Rather than doing this manually, how you can analyze this is by using the receiver operating characteristics, right? So let's do that actually. So let's use this library. So with this library, what we can do here is basically to plot this graph of your true positives versus false positives to understand what is this number that will be suitable for you, right? So I'll show you guys exactly, and some use cases as well. Depending on the use case, this number might change, so which I'll show you. So first things first, let's create ROC predictions. So ROC stands for receiver operating characteristics. It's basically going to help you to find if given model has a good accuracy or not. So let's go ahead and give the predictions. My predictions are going to be my prediction test. My actuals are going to be my test admit. Those are the two variables that this needs. So my prediction is done. My ROC performance, so that is equal to, so ROC performance. So that's going to help you to find the performance of this model on the test data. So here, if you see here, it needs the predictions. I'm just going to put my ROC prediction here, right? And then I'm just going to say how do we want it to get it predicted. I'll just say TPR, right, comma FPR. So I'm just going to understand these predictions plotted against my TPR and FPR. So let's just run that, and then let's also create another performance metric, area under the curve. So I'll just run this, and then say instead of the TPR FPR, I'll just call it as AUC, right? Perfect. So let's also run this one. First things first, before analyzing these performances, let's take it one by one. Let's take the first performance here and plot this the ROC performance, the true positive and FPR rate. So if you just run this plot and then put the performance here, it's going to show up the receiver operating ROC curve. So if you see here, you have your false positive rate on your x-axis and you have your true positive rate on your y-axis. The problem with this curve is it doesn't have the actual meeting points, like where does my TPR meet with my FPR, right? I want these numbers. To get that, it makes it much easier to analyze. Just say print.cutoffs by 0.1. Every 0.1 will have a print, and then it will range. It will also increase by 0.1, right? So let's just put that, and then it looks a little bit boring now, so let's just colorize that. Alright, so once I run that, colorize, oops, Mr. L here. So I'll just run that and it's gonna be a lot better now. So perfect. So if you see here, I wanted to always make sure my true positive rate is highest as possible, right? Because false positive rate is a misclassification. True positive rate is a correct classification. I always wanted to classify it correctly or predict it correctly. So I always wanted to have it as high as possible. I should also not, compromise on the higher FPR rates, right? So if you see here, when I choose, let's say if you choose 0.5 as my number here, for my predictions here as my 0.5, what's going to happen is it's gonna give me a average TPR rate, but then I'm reducing my correct predictions, but my false positives are like super low, right? But then if I go a little bit high, if I wanted to have a better TPR, so like 0.3, if I choose 0.3 as my threshold, right, what's going to happen is my TPR rate is really high, like I have an amazing TPR, but then what's happening is I have my false positive rate is also increasing. So it depends on the application. Let's say if it is a healthcare application, if you wanted to predict a patient to be sick or not sick, what you will say here is you always wanted to make sure you're having a obviously true positive rate as high. You always also wanted to make sure the false positive rate as low as possible, because you don't want to classify a person as sick but he's healthy, right? So that's a problem. However, if you take a different application in which you are just predicting, in this case, just a student admission, which is not a life and death situation, it's just a predicting if the person is getting admitted or not. In that case, you can take a risk of having a little bit higher false positive rate also, by having a higher true positive rate and having a good false positive rate also doesn't make a big difference, right? So that's a trade-off here. That's a decision that the business will take at this point, what they wanted to choose, what threshold they wanted to keep. So next thing what we can do is to find the area under this curve. So that basically shows the accuracy. The more the area under this curve is, the better the accuracy of the model is, right? So the ideal value is going to be obviously 1, which is basically if a curve looks like this, right? Which is a very ideal scenario. None of these curves is going to look like that. But then our thing is to basically, we have a diagonal line here, 0.5 line. So we always want to make sure the curve lies above that line, right? At least it will have accuracy of more than 50%. So now let's find this area of this curve by running this RSC performance variable, then saying add value, just go to the y values. See here, that's gonna basically show us the area under this curve. So 0.77, which is a very good value. So yeah, I think this model is looks good by having it as having this code as 0.3. So what is going to be my threshold in which I'll be deploying my model. So so that's what we have here, guys. So let me know if you have any questions or comments. I'll see you guys in the next video.